Ladies and gentlemen, good morning. In this video, we will be talking about the Lagrange equations and how we can get the equations of motion of a system with two masses, a spring and a non-conservative force. So this is not a derivation video where we show how to get the Lagrange equations, we just apply them. So let's jump right in. Let's look at our system first. We have mass 1 that is gliding along a rod that is fixed with the angle alpha relative to our x-axis. Then we have mass 2 that is attached like a pendulum to mass 1. And on mass 1, we have an acting force F. This is our non-conservative force. And of course, not to forget, we have a spring that is attached to mass 1, and it's either pushing or pulling, that is attached to a fixed point in space. So this is the system that we have. And now our first step is to find our goal is to find the equations of motion. And to do so, we have to first get our generalized coordinates, so our actual degrees of freedom. If we look at our system, we see that mass 1 has only the option to glide along the rod that we have, and the distance is set with s. And mass 2 is just a simple pendulum that we had in all the exercise before, where the angle beta is the only one that's determining the position of the mass 2, because we have this relative to the x-axis, and by knowing the angle, we know the position of the mass. So we have two coordinates that we need to know, two generalized coordinates, our q's, that is s and beta. Now we just have to follow our simple recipe to get the equations of motion. First, we look at mass 1. So our goal is to get the kinetic energy and the potential. To get the kinetic energy, we first have to get the position of mass 1. So if you look at mass 1, we have a cosine alpha times s and a sine alpha times s. Because we want the velocity, we need to derive it with time, and we get s dot cosine alpha and s dot sine alpha. Now we know that the kinetic energy is 1.5 times m times velocity squared. And because we have vectors, we do 1.5 times m1 times r1 dot transposed r1 dot. And we get our kinetic energy. To get our potential, we have minus mass 1 times gravity times the cosine. Because if we increase our s goes up, our whole potential goes down. That's why we have the minus. So this is all we need for mass 1. We get the kinetic energy and the potential energy. Now we have to do the same thing for mass 2. So let's look at the position of mass 2. We have, first of all, here the same position just like mass 1, but then we have an additional term because we have this pendulum. After we have the position, we again do a time derivative, and we get our velocity, our absolute velocity of mass 2. Then we again get our kinetic energy by 1.5 times m2 in this case, r2 dot transposed r2 dot, and we get this lengthy expression. Now we have to get the potential energy of mass 2, and we have minus m2 times gravity times the position along the x-axis. So this is fairly simple. We just have to get the kinetic energy and the potential energy. And this is everything we have to do for mass 1 and 2. But then let's not forget that we also have another potential, and that is the potential of the spring. Let's look at our system again. Let's get rid of this. So we have a spring that is pulling or pushing mass 1. And this will have an effect on the equations of motion. And that's why we need to consider it. So because the rod is not on a 90-degree angle, so this is not 90, we can't apply Pythagorean theorem right away. We have to do a little bit of extra work to get it to that point. So we have h, that is the distance from the origin, that's right here, the distance from the origin to point A, and we have to project our distance s into cosine and sine. And now we have this length, and we can square it to get L squared. So this is what's happening right here. We have basically a squared plus b squared is c squared. If we remove the parentheses, we get this expression, and if we want just the length, we can just take the root of that. Then we know the formula for the potential energy of a spring. That's 1.5 times c times L minus L0 squared. Don't forget the squared. L0 is the length of the spring where it's not in tension and not in compression. So this should be given when you look at the system, and we have it right there. The next step is to sum up all the kinetic energy and sum up all the potential energy. So now we have the total kinetic energy and the total potential energy, and we need those later. Now let's look at our non-conservative forces. Because we do a projection when we derive our kinetic and potential energy with our q's and q dots, we also need to do a projection of our force. So we have a force, and we need to project it into the directions compatible with the constraints. And just like in the virtual work principles, we have the directions compatible with the constraints. We will get that by deriving our position, where the force is attached to or attacking, and derive it with our q's. So we need to find du, dq, the position where the force is acting on is R2. So we have R2 dq, and we derive it now with our q's. So here we have R2 derived with what was our q's. We have s and beta. So we have dr2 ds and dr2 d beta. After we have this, we need to transpose the matrix, because we have a transposed right here. Oh, that is already transposed, so we get rid of that. So we have this matrix, and now it's a simple matrix vector multiplication, and we get our projected force, our projected generalized non-conservative force. The last step is just a derivation. So we have the absolute time derivative and a partial derivative of our kinetic energies with our q dots minus the partial derivative of our kinetic energy with our q's plus our derivative of the potential energy with our q's. Don't forget the transposed, and this will be equal to what we had right here. So at the end, we will have two equations of motion, not because we have two masses, but because we have two generalized coordinates. And this is everything you need to know when you apply the Lagrange equations, that you first get the total kinetic energy and the total potential energy. If you have non-conservative forces, you need to project them by getting du dq transposed and multiplying it with f, and then just do a simple derivative and set it equal to the non-conservative forces. I hope this video gave you a better insight on how to work with the Lagrange equations. You see that this is not a lot of work. It's way better than the principle of virtual work. If you have any questions, feel free to ask them in the comments down below, and I'll see you next time.